Okay, so now we start with chapter 2. It's Heaps generating function. So you remember there was 3 basic lemma, where all the course is based on 3 basic lemma, and this chapter will give you 2 of the 3 basic lemma. First basic lemma, the generating function for heaps, extension of the generating function. For heaps, there is a certain constraint on the maximal piece. And second lemma, the logarithmic lemma, what is the logarithm of a heap. But I claim that this lecture, this classes, is independent of the classes last year, which were devoted by introduction to enumerative combinatorics. So I will repeat chapter 2, maybe in a shorter. I will repeat chapter 2, and if you want more detail, go to the video of last year. So first, I am going to define an ordinary generating function and formal power series. So what is the intuitive idea of formal power series? I suppose maybe you know very well what is a formal power series, generating function. Maybe you have a vague idea. So for beginner, I make an intuitive introduction to formal power series and ordinary generating function. So this is the famous sequence of integer, 1, 2, 5, 14, 42, etc. This is a Catalan number, which appear everywhere in mathematics, in physics, in computer science. So to this sequence of numbers, you can put some variable. You put t, t2, t3, t4, t5, and you get a polynomial if you stop at degree 5. If you don't stop, then plus point, and then you get a formal power series. Formal power series, just a polynomial intuitively, where you can stop anywhere, you can go to infinity, and this is a formal power series. Or this is called the generating function for Catalan number. Each sequence of number has a generating function like this, and t is a formal variable. So in combinatorics, we don't care about the convergence. If you put t equality number, maybe some formal, the generating function over n factorial, the permutation, if you put t any real number, then it's going to be infinity. But we just do things formally. So you have a kind of generating function, and maybe it can be, you can use analysis, it can be a function of analysis, but for combinatorics, everything is formal. So a few examples, a few exercises. 1 over 1 minus t, 1 plus t plus t2 plus t3, because if you multiply this infinite things by 1 minus t, the term is going to cancel 2 by 2 and you will get 1. So a little exercise. What is 1 over 1 minus t plus t2? So t plus t2 equal u. So it's 1 plus u plus u2 plus u3 plus u4, etc. And you replace u by t plus t2. And you get 2, 3, 5, 8, 13, 21, which is a famous sequence. And this is the brother sequence. Catalan and Fibonacci numbers appear everywhere. Why? You see, so let's take the computation. So 1 plus u plus the square of u plus the cube of u, etc. So we say you have an infinite term appearing, but if you look carefully in each column, you collect all the term in T2, all the term in T3, in T4, what you get in each column is 1, 2, 3, 5, 8. You get the Fibonacci numbers. So see, everything is done formally, but you have a lot of freedom compared to real analysis, but freedom is good when there is some limit, some rule. If you have no rule at all, then you are lost. So this is nonsense. T plus t plus t plus t plus t plus t, or 1 plus 1 plus 1, this is forbidden. There must be a formal convergence of the formal power series. So let's take the formalization of this. So formal power series, it's a certain algebra, it's an algebra formal power series. So the coefficient, I will have some coefficient, it can be like a Catalan number, Fibonacci is integer, but in usual, it will be a commutative ring, which can be numbers, integer, rational, complex, or even I will have coefficients which are polynomial in integer coefficient with alpha, beta, gamma. I will have some formal power series where there is some parameter alpha, beta, gamma. If I want to count something according to a certain size, like the Catalan number, but with some parameter. And then I will have some extra variable, which are again formal variable. So here is a certain power series. This is a polynomial algebra of okay, this is a notation, and the ring of formal power series is denoted like this. In one variable t with coefficient in k, and you have an algebra of formal power series, where you can define the sum of two formal power series, the product, and the product by a scalar. So if you have two f and g, two formal power series, then the coefficient h of this result I denoted by Cn Tn, and then you have a I forget the slide. I see here. So the sum is Cn equal An plus Bn. The product is like the product of polynomial. The product of the term Cn is all the sum of product AP B cube for P plus Q equal N. And the product by scalar is just Cn equal lambda An. So with these three, the sum, product, and product by scalar, you get a vector space. In fact, you get an algebra, the algebra of formal power series, which is an extension of the algebra of a polynomial. And so I define the generating function for any sequence of numbers, or any sequence An or anything. I can define the generating function, or usually it's called the ordinary generating function. In this class, I will use, except for one exception for 10 minutes, but I will use always ordinary generating function. There is some other function like exponential generating function, meaning you put Tn over n factorial. But everywhere here will be ordinary generating function. This is another kind of function, exponential generating function. So definition, family is summable if and only if the sum, say you have a certain family of power series, Fi of t, and I will say it's summable if and only if, see, for every n, the set of integers such that the coefficient of t power n in the power series Fi of t is non-zero, this set is a finite set. You have a family, infinite family of polynomial or formal power series. If you collect for each of these Fi, you collect the term t power n for a certain n, you sum all these terms, then the sum is finite, and it's a finite set of such term. Example, you see, here, I have an Fi is t plus t2 to the power I, so I have an infinite family of function Fi, but if I collect the term in t power n, then I have only a finite number of terms which contribute to t power n, and this for any n. So I can define the sum. So I repeat the definition. We have for each n, there is a finite number of Fi which contribute to the term t power n. So this defines you the sum of the Fi. Example, if you take this family, An-Tn, this family is summable because there is only one for each term Tn, and so this is a justification of the notation. Now this notation, which are just formal notation, it now is a real, corresponds to the definition of a summable family. And you have and equivalently, you have also the kind of infinite product. If you take this infinite product, if you take the product of all this, if you collect, by taking the rule of product of a power series, if you collect the term in t power n, then there will be a finite number of elements in I which contribute to give you the term in t power n. So this defines precisely what is an infinite product, and a very nice example is this, the product of all the 1 over minus qi, which is a famous generating function, the generating function for partition. We have seen last time quasi-partition. So this is unusual to start a class with quasi-partition and then start now to give the example of partition. So some other operation, which correspond to the same operation in analysis in classical function. There is substitution, and you substitute, you see, you replace t by the generating function g, but to make sense, then the coefficient b0 must be 0. The generating function, the power series g must start with coefficient t, because if there was a constant here, when you replace, then the constant of term will be, you have an infinite sum of constant term, and this is not allowed. So there is the inverse. We have seen, so you can take the inverse of the generating function. The order means the degree of the term of minimum degree. So the constant term must be 0 also here to get to make sense with it. You have the derivative of a function, just like derivative tn is n times a1 tn minus 1. And there is some classical, other classical definition, like the exponential, the logarithm. You can replace t by a power series, or the binomial coefficient, you can take 1 plus t power alpha for alpha any numbers. It can be integer or rational number. Just to formally you write this. And exponential, logarithm, power, all these classical operations in analysis or in polynomial, you can do them in formal power series, but there is some condition to be able to define it. For example, exponential of f, the constant term of f must be non-zero. And then, I don't know if we will use a lot of things, a lot in this class, but there is formal power series with many variables. But there is also the partial derivative. I will not use too much of this. Always the class will be formal power series with one variable and coefficient in a ring of polynomial with extra variable, which are the parameters. So there is a so-called symbolic calculus, symbolic method in combinatorics. In the old time, we are doing counting things. You have to make a recurrence relation, then to transform this into a functional equation, etc. Now you can, from the combinatorial object, from the structure itself of the combinatorial object, you can directly get an equation for the generating function without going through recurrence relation. So this is called the symbolic method. This is a modern way to do enumeration combinatorics. And I will intuitively give you an example with partition of integer. So a partition of an integer is like this. It's a decomposition of the integer into decreasing, weakly decreasing sequence of numbers. It is visualized as a Ferrer diagram. Ferrer diagram on each element. In each row, you see there is 6 element 6. Each element of each row is a part of the partition. So some people like to make Ferrer diagram partition with square. Some people prefer to make point. This is another Ferrer diagram. And then there is a generating function for partition of integer. So here I am counting the partition of 1, 2, 3, 4, 5, and the number 1, 2, 3, 5, 7, etc. So the generating function is this formal power series. For some moral, philosophical, and historical reason, we put a Q instead of a T. I will explain maybe why Q is there is the Q analog, the Q hypergeometric function, and now there is a Q combinatorics, which now rejoins, there is a quantum mechanics, and the two Q come together into a nice combination of Q series and Q quantum. So what is the generating function for partition? Instead of doing brute force to give you the formula for the generating function, I am going to apply this symbolic method calculus without defining it. I do it on an example partition, and after you have seen this, I will make the formalization of this symbolic calculus. So first, when you have Ferrer diagram, there is some row. So this is a row with I point. What is the generating function of rho with I point? It's q power I. So a single term. Now I am making rectangle with I column. What is a rectangle in the Ferrari diagram with I column? It's the sequence of rows of the same size. There is a lemma now in the symbolic calculus which tells you if I have the generating function of an object, like q power y, then the generating function of sequence of the object is 1 over 1 minus the generating function of the object. So that's 1 over divided 1 minus qi. Now a Ferrari diagram is just a decomposition into a product of rectangle. I have a disjoint here. In fact, it's a Cartesian product. It's the set of this. It's isomorphic to a product as a Cartesian set of a rectangle of with 3 columns, a rectangle with 5, rectangle with 8. But formally, it's a product of rectangle with 1 column, 2 columns, 3 columns. Maybe there is no rectangle with 1 column. It's empty. But when I do this, 1 over 1 minus q, then I include the empty rectangle. It starts by 1 plus q power y plus q. So the empty rectangle is included in this generating function. And so you can decompose as a product. The Ferrari is a product of rectangle. So you see, in the old time, when I was, all my life, I was working with transparencies. We don't have this new technique since 10 years, but before we were overhead projected transparency, and you have to be good with your hand to do this. So here you can check that there is some transparencies which are empty. There is no rectangle, but you have all rectangle of size 1, 2, 3, 4, 5. And so, applying now the second rule of symbolic calculus, product of rectangle means product of generating function. Okay, so the generating function, this is the generating function for Ferrari diagram having at most m vertical. So the parts are bounded by m. There is a rectangle have a size at most m column. Now if you take the limit, product, infinite product of this. No problem. So this is a generating function of partition of integer. The infinite product, p over I, of 1 minus. Of course, in some homework or school, you can say, okay, take this, expand in formal power series, and prove directly that the coefficient of q power y is going to be the number of ways to decompose. And when I was a student for going to some school, there was an exercise. We have to prove directly that and the coefficient. But now you know standard technique, sequence of object, product of object, union, and for the logarithmic lemma, second basic lemma, I will need the derivative. And all this can be, instead of putting this at the level of analytic calculus with derivative function, we can put this at the level of cometal object to define the sum, the product, the derivative, the integral of a cometal object itself. This I will do in the next section. But before going to the next section, the exercise. So example 1, instead of taking all partition, take partition such that the part belong to a certain subset I, which is given. You give any subset I of the integer, and then the set of a partition such that the part are equal to this is this restricted infinite product. Oh, it's easy exercise. I want you very easy. Huh? This is important because in the famous, we will meet in this class, the Roger-Ramanujan identities, and they involve such numbers equal to 1 and 3 modulo 5 and 2 and 4 modulo 5. And the famous Roger-Ramanujan identity involve also the so-called D partition. So this is exercise 2. The D partition is a partition such that the difference between two consecutive parts is bigger or equal to 2. So the exercise you have to prove the generating function, this is in French, the generating function of D partition is this summation. So it's the same in product as for partition, but there is a q power m to the square. And sum over all m of this.
The denominator being square?
Denominator? No. If you put a square in the denominator, what do you get? there is a famous identity. I will prove it if I have time at the end of the class, or I will prove it next week. If you put a square of the denominator, what you get is exactly this. That is, you get back derivative function for partition, and there is a nice proof of this, which use again symbolic calculus. So if you take the square, it's very easy, it's partition. If you don't take the square, then this is much deeper, this is the Roger-Ramanujan identities. Very deep. No nice direct bijective proof of this Roger-Ramanujan identity. So exercise 2, I give you a hint, it's find a bijection. You see, in this class, many exercises find bijection. It's because it's my favorite point of view, is to do bijection. So there is many exercises with finding bijection. Maybe you are not used to do bijection, but if you are very good in bijection, very good in analytic calculus, then if you combine the two techniques, then you can solve conjecture, or you can be famous. So you have to learn bijection, which is less classical than the classical calculus. So the hint for the exercise is find a bijection between partition of n with at most m part. So the Ferrari diagram is bounded at the height m, and departition of n plus m to the square, having exactly m part. So this is not too difficult to find, and if you find this bijection, then this gives you a proof of this. You start, because you know the derivative function of partition having at most m part is the same as the derivative function of partition such that the parts are bounded by m. This was the finite product of just before. And from this finite product, to multiply by q power m to the square is going to be given by this bijection. So there is a shift between partition of n and partition, so you have to add a new, some m to the square to the Ferrari diagram. So this was the intuition of the symbolic calculus. Now I make a formalization on this. Formalization of the operation on commutable objects, the sum, the product, and sequence of commutable object. So definition, I want to formalize an intuitive idea of what is a commutable object. Is it a finite simple group? Is it a commutable object? Or Lie algebra? Is it a commutable object? So there is a simple axiomatic to formalize this idea to make the sum of two commutable objects, the product, the sequence, the derivative, the logarithm, etc., etc. So it's possible to define operation at this level of commutable object, which, when you take the generating function, which project at the analytic calculus level. So it's more powerful to work in the jungle, the forest of commutable object, because once you project analytic calculus, then you are on the flat level, and you lose a lot of information of the combinatorics. So the level of commutable object, the level of bijection, the level of all this. So we make a formalization. I will need to make generating function of, like for example, the second basic lemma of Heaps, the logarithm of the generating function of Heaps is going to be related to the generative function of pyramids. I need this formalization of the derivative of a commutable object. I can take the derivative of a Heaps. I can make the integral of a Heaps. I can make many things at this level, which project at the level of a classical analytic calculus. So definition, we take a class of commutable object. It's just a pair AV. A is a finite or enumerable set, any set, and V is a weight, a valuation. So to each element of this, which is going to be commutable object, I associate a polynomial. So X will be the formal variable, so it will be alpha, beta, gamma. It will relate to the parameter I want to count. So it's polynomial with, again, coefficient in a certain ring K.
What do you mean
each object is going to be weighted by a certain polynomial. For example, when I want to count object of like partition, for example, with n part, then the weight will be t power n or q power n. Each cell of the row was q power I. Each red point was weighted by q. So my Ferrier diagram were weighted by q power the number of cells. So this was the weight, this was my combinatorial object. But in general, so I take any set, to each element of the set, I associate a weight, which is going to be a polynomial. In general, it's going to be t power n, to have an object of size n. And then some extra, maybe alpha, beta, gamma, alpha power I, beta power something, which is to be counting the object of size n with certain other extra parameter. Okay, so definition, again, I have a finite or enumerable set. I have a weight, any map, sending an element of A on a certain polynomial with variable x, and coefficient in k, in general k is the integer, and there is a condition. So that I am going to define the generating function. I am going to define the infinite sum. The sum over all objects of this weight must make sense. So to make sense, I have the condition star. For any monomial in this weight, I take the set A index W, all the objects in A, such that the coefficient of W in V of alpha is non-zero. I take this set, so I take all the objects which contribute by their weight to the word W, to the monomial W. For example, it's for the partition of integer with the weight q power the number n, the number of cells. I fix n and I take all Ferrier diagram contributing to q power n, so there is a finite number. It's all possible partition of n. And condition star tell you that then, if once I define this set, then for every monomial, this set is finite. It's analog to the definition of summable family of power series. You fix a certain integer k and you take all generating function which contribute to t power k, and there must be a finite number of such a things to be able to define the sum of all this. But here's a little more complicated. I make the general case. Instead of taking the monomial to be only t power k, I take a monomial to be any polynomial in several variables and coefficient in k. So this set A index W is all the objects which contribute the coefficient of W. This weight maybe is a sum of the weight can be a sum of monomial. It can be a sum. It can be q power 3 plus q power 5. But the one who contribute to W must be finite. And so I will say that this weight is summable, and definition, then I can define the generating function of such object. F index, the class of object weighted by V, is the sum of the weight of all the objects. And this sum makes sense. In particular for heaps, I will have some weight. I weight each heaps, and I will be able to define the sum of all the weight of all the heap. And then I will give you the first lemma, will give you a formula for this sum of the weight of all the heap. So the family, this family in the sense of the summation of generating function is summable, and this makes sense. And this will be the generating function, generating power series of the object of A weighted by V. So some example of this, it's for example, if the weight is t power n, any object at a certain weight, which is a single monomial in variable t, then I can say, okay, n is the size of alpha, even if alpha is not composed of any cell, any point in the edges. This is the abstract size. As soon as the weight is t power n, I will say, okay, my object has size n. An is in the notation, is the cardinality of the I index by this monomial, the number of objects having size n, and then the generating function, in that particular case, become the generating function an t power n, where an is a number of objects of size n, even if I have nothing, I have no size, no cell, no point, no edges, it's just abstract size of the object. Or more generally, I can make some extra variable. So you have the size, you have the variable t, which is going to really to compute the object with the size n, and then an extra weight to have extra variable if you want to count more by more parameter, where wi is a certain monomial in the variable y. And so I have I will have many in this class, many generating functions like this, where t is going to count number of heaps with number of pieces. For example, heaps of diamonds. T will count, there will be a t for each diamond. And if I take a diamond I plus 1, then I can put q power I. And exercise, what is the generative function for semi-pyramid of diamonds with a weight q power I multiplied by t? And if I put t equal 1, or t equal minus 1, if I take a weight for each diamond equal minus q power I, and if you take semi-pyramid of diamonds, the sum of the weight of all this will be the Ramanujan continued fraction. Chapter 6, chapter 7. So you see there is many different weights with many different heaps, many different pieces. Will give you plenty of classical function in analysis or in beautiful function and beautiful Q analog and many things. So this is maybe abstract for you, but wait, the menu you will have many beautiful things is coming in the next. So go back to the abstract things of the symbolic calculus. You can define the sum of two objects. If you have two classes A and B satisfying the condition star, then the sum is a Dijon union, and it corresponds to the sum of generating function. Dijon union, so this is very easy to see. You have the product. Product is a Cartesian product, such that the product, the weight of the pair alpha beta, when you have a pair which is a Cartesian product of A by B, then the weight will be the product of the weight. If the weight is t power n, the size, then the size of the product is the sum of the size. This was the class last year, so I did not define the binary tree, but and the lemma corresponds, the generating function of the product of object is going to be the product of the generating function. And for Ferré diagram was the product of the, in the case of Ferré diagram, the weight was q power, the number of cells of the Ferré diagram, and I have this condition star and everything. And the last lemma I used today was the sequence of objects. Sequence, it's first you have nobody, then you take the objects themselves, then the product of A by A, product A3, AN, etc. Sequence is an order sequence of the object. You take a pair, a triple, etc. So we have seen that a rectangle of size I colon was a product, a sequence of row of size I, which give you 1 over 1 minus q power I. So this is symbolic method of a flageolet, and so it's 3:20 until 3:30. Is the room I have to finish at 3:30 sharp, or is there somebody else? So I have time to do the dig pass. So we have seen dig pass, I think last time, some exercise. So a dig pass is a pass in the positive integer, in the square, in the quarter of this lattice. So it's a sequence of points, starting at the point 0, 0. These black points are always above the 0 level. And you can go elementary step between two consecutive points. You can go northeast, the next neighbor, or southeast to the next neighbor. And then so you go up, down, up, down, up, down, up, down, etc. And at the end, you go back to level 0. I claim that it's very easy now to enumerate this dig path by using symbolic calculus. So just take the first time the path, go back to the origin. This always exists, because at the end it must be at the, go back to the 0 level. So this is the first time. Maybe it can touch many times. So we have a blue step. This blue step corresponds to this blue step here, and then you cut it here, you see. There is nobody here. So what you get here is again a dig path. What remains after this blue step is a dig path. So I have decomposed my object as a product of 3 objects. The 2 blue steps, this dig path. So if I count this dig path of length 2n, there is an even number of steps according to only n. For example, the number of southeast steps, then I get this algebraic equation. The dig path is empty, or maybe it's decomposition. This is count for t, y, and y. So you have the product of 3 objects, 2 dig paths, and then 1 edges, which is weighted by t.
You should mention that the weight is 2 times.
The weight is t power n, where n is the number of southeast steps, or half of the total number of steps. The path is even length, so it's 2n, and n is half of the length, which is the number of southeast steps, for example. And so the number of dig paths is a Catalan number. Why? So I have given straight away this algebraic equation from symbolic calculus. Usually in the old time, people were giving recurrence relation between dig paths of size n with dig paths of smaller size. But this recurrence relation, if you know the product, the definition of the square of a generating function, this is equivalent to this with the initial condition. Now, if you can solve this, it's a quadratic equation. Do at the primary school square root of something, and if it was real number, so you have this, it's plus or minus the square root of this. If you put plus, then you are a problem because it's not, it's begin by 1 over t, so you have to pick minus. Expand this as a binomial 1 minus u power alpha, as if it was an integer. If you expand it, then you get this infinite power series. And if you replace u by this one, and u by minus 40, and m by 1 over 2, then you get the very classical formula for Catalan number. So it is, they are everywhere in Catalan number, 1 over n plus 1, 2, and 2. Then, so Catalan is Eugène Catalan. This is a paper in 1838. And you see, you have the recurrence relation. There was no generating function too much at that time. He has many papers about Catalan number, but who introduced Catalan number? It was Euler, a long time ago. Euler introduced this, but he introduced this not as dig path, but as triangulation of a convex polygon. This is the last part of the letters he has sent to his friend Goldbach. Goldbach in number theory is very famous for Goldbach conjecture. So he's counting, you see, this is the 5 possible triangulation. Here, this is a Catalan number. Here, this formula, here, this product by product, in modern terms, this is this. Now we have a Catalan number. Now we have now we introduce generating function, formal power series. At that time, everybody blamed him because this is nonsense. If we put a equal a number, it may not make sense. So at that time, then Gauss, everybody after came, you have to be rigorous, the convergence, the radius of convergence, everything. But Euler was a pioneer when he introduced formal things. And you see, he has exactly what we have seen from the quadratic equation. He has exactly the generating function. Even he compute for a equal 1 over 4, which is a pole of the fraction. Singularity, essential singularity of this is 1 over 4, so he was starting analytic combinatorics. This is related to asymptotic. It's very, and you see this letter, 1751. And this letter, it has written another paper. You see triangulation of a polygon. And this paper, in fact, has nothing to do with Catalan number and triangulation. This paper is counting the sum of the angle of a polygon, which is preparation for the sum of the solid angle of a convex polytope. And in fact, he was working with convex polytope and his famous formula, number of vertices minus number of edges plus. So the two was related. And okay, I go a little fast to give you an exercise. So the binomial, there is a bilateral dick path, which we have seen last time that it's 2 and 2 then, it is obvious. Bilateral dick path coded by this bilateral dick word, a word in 2 letters with the same number of x and x bar, which is the binomial coefficient 2 and 2 then. And exercise, so find an algebraic system of equation for bilateral dick path and deduce that you have this generating function. So this is an exercise, and I have 5 minutes more to give you another IS 25. I can continue? No, nobody? Okay. So let's go back to HIP now. You remember there was an exercise on find a bijection between quasi-partition and heaps of diamonds. And in the special case where you have a semi-pyramid, this gives you a dick path Catalan number. So now we are going a second exercise to give another proof. So here is a semi-pyramid of diamonds on N. It's a pyramid, a unique maximal piece, see project at 0, 1. And from exercise 2, the last chapter, we know that there is a bijection between this and dick path. So the number of such semi-pyramid is the Catalan number. This was the exercise of last time. You can check 1 semi-pyramid, 2, 5, 14, etc. Now the exercise, I will give you a second proof with algebraic equation by using the technique of symbolic calculus. So here is a semi-pyramid, and I am going to show you directly that on this heaps, it satisfies the algebraic equation the same as for dick path. So in the first column, look, maybe there is only 1 diamond, maybe there is nobody here, maybe there is somebody. I take the topmost of the diamonds, which is not the maximal piece, in purple. And then you push down this. If you push down, look carefully. What you get is, again, a semi-pyramid. And so your semi-pyramid has been decomposed into 2, in this semi-pyramid and this one. And so you get this algebraic equation. So this is another proof, direct proof, to decompose the semi-pyramid into here a blue diamond, which is going to give you the T, and this is Y, and 1 in case there is nobody, there is no empty semi-pyramid. Yes?
At the 5th level, I think it should be on the 4th level.
What? I don't understand. What is the question?
The dimer at the 5th, the piece at the 5th level.
Level 5, yes?
Should fall.
This will fall.
Ah, yes, it should fall, yes. Mm-hmm.
But it's okay. You push down. See,
Yes, it should fall, okay. Yeah, but it's the
still
same.
you push down from the next one.
Mm-hmm, mm-hmm. Yes, again a mistake. Okay, good. Thank you for I will correct the transparency, but this one will not go inside this one. Even if you put it here, then pushing it.
It won't get pushed.
Mm-hmm. So this is a assay diagram. In fact, my semi-pyramid is just everything which is below this maximal piece. In terms of poset, I take everything below, and what remains is another poset. And so the conclusion I have: the dick path has this algebraic equation, the pyramid has this algebraic equation. So exercise, give a recursive construction of a bijection between this and this. It's possible because if you associate, you see, you have decomposed into 2 pieces. So if you associate these pieces to this one, you associate these pieces to this one, then recursively, by decomposition of pyramid and dick path, you can get a bijection. exercise, if you have a computer scientist and you think recursively, compare to the first bijection coming from quasi-partition. It's the same, I think. I feel it's the same bijection.
Oh, you don't know?
Yes, I know. It's an exercise. Maybe, you see, I made some mistake. Maybe I am wrong, but... and then I will finish with pyramids now. Pyramids of dimers on the up to translation. Pyramids of n dimers. So we have seen in exercise 3 of the last chapter that it was in bijection with bilateral Dick pass. I ask you by using again the kind of idea of the lexicographic normal form or Knut normal form. So, and you get the number of pyramid up to translation is half of 2n. And now the exercise is to give a second proof with algebraic equation. So exercise, find an algebraic equation for Dick pass, algebraic equation for this, and get a proof of that it's the same system of algebraic equation. Okay, I think we can, maybe I will do this next time. Okay, so that's the end of the class. Thank you.